Well, thank you very much for inviting me here. I feel it's a little loaded having to follow Paul Money as a speaker. How do you follow Paul Money? In fact...
No, you're rubbish.
It's never been rubbish in my opinion. But,
yeah, it does. Yeah.
Anyway, so this talk is on metals. So this is something, it's not really an expertise of mine particularly. It is one of the people in our department, so I've learned quite a lot sitting next to him and discussing this sort of thing. So I thought, well, let's not waste the material, let's put it into a talk. So let's start the three questions which were alluded to. Metals, what are they? At least in terms of astronomical things. How are they made? And what can they tell us? Everything okay there?
We're trying to get it a little bit more like...
Right, oh, fine. Yeah. So I thought I'd start with the periodic table, because this is what chemists start with. This has got all the elements on it. There we go. So there's quite a lot of variety, obviously, for elements, from gases to liquids to solids and all that sort of thing. But we just wave our hands in physics at chemists and say, well, just get on with it. We know what's the real deal. But metals are generally thought of as hard, opaque, shiny, good conductors, that sort of thing. This is what you kind of learn in school as what a metal is. And this is kind of how they lay it out in the periodic table. So all these things in blue, chemists consider metals. They're a bit dubious about exactly what hydrogen is, because that sometimes appears as a metal, sometimes not. And these things over here are non-metals, and these things over here are somewhere in between. It says here they're metalloids, but semiconductors or semi-metals or something like that is kind of what they're often called. So that's kind of the basics that we learn in chemistry and kind of what a lot of people think of as metals. When I was looking at this, I was looking for a periodic table and typed in periodic table metals, and I found all sorts of things. So this is one of them. So this is a periodic table of metal bands. So you can see Deep Purple, Led Zeppelin, and so on. Now, I don't know if it ever happens to you, but have you ever been late at night typing things into the computer, got to a Wikipedia page, followed a link, followed a link, followed a link, gone to a YouTube, and before you know it, it's like 2 a.m. and you've discovered a whole lot of rubbish. Well, this is what happened with me. So here's a periodic table of classic rock. But there's actually a whole genre of periodic tables. Here's one of music notation. Okay? Here's one of irrational nonsense. And perhaps scariest of all, here's one of business lawyers. So this sort of sent me off on a rather winding path one night, so I managed to get back. They've even got booze here, so there's all sorts of things. So anyway, I urge you not to go too far down the periodic tables, because everybody seems to be jumping on the bandwagon there. But let's get back to the topic in hand, and this is the astronomer's periodic table. We have hydrogen, we have helium, and everything else, and that's just as simple as it can get. And there's a good reason behind this. As you saw from the chemist's periodic table, nearly everything is a metal anyway. There's just a few things over this side that are non-metals and a few funny semiconductors. Everything else is a metal. So that's kind of where this came from. They said, well, yeah, by and large, everything's a metal, so we'll just lump everything in together as metals. The other thing is, this is what the universe consists of. So about 74 and a bit % hydrogen, 25 and a bit, they don't add up, do they? Well, probably not. So it's nearly all hydrogen, about a quarter helium, and the metals are this tiny fraction here, 0.2% is about what we reckon is stuff that isn't hydrogen and helium, at least of atomic things anyway. There's a whole other talk I could give you on dark matter and things like that, but we'll stick with stuff we know for this talk. So this is also why they have this periodic table with just hydrogen, helium and metals, because really when you're looking at the universe, it's all hydrogen and helium and then some random stuff. This random stuff is really important because, you know, it's what the Earth is made of, it's what you and I are made of, and it's the air we breathe and all that sort of stuff. So it's really important to us. But on a cosmic scale, it's not. It's just a really tiny fraction. We're a sort of flotsam of the universe. And this is how much we started off with. So from the Big Bang, it was all hydrogen and helium and almost infinitesimal bit of lithium and nothing else. So that's where we started from. Obviously, we've got to where we are now, and we've got oxygen and carbon and nitrogen and all those other elements that we know and love and rely on to keep us alive. So they've got to come from somewhere. So where do they come from? Just to give you some background, so here's some basic nuclear physics. I hope I'm not talking down to anyone when I'm talking nuclear physics, but we'll just get the grasp of what nuclear physics is, and then you can all go off and build atomic bombs or something. But we start with the two basic particles. So we have a neutron and a proton. These are the two building blocks of atoms. And protons are really important ones because they give the elements their flavour. So a hydrogen is one proton, and it really doesn't matter how many neutrons it gets. It's always a hydrogen if it's got one proton. So that's the basic building blocks of particles. There's also electrons and other things, but we can sort of discard those for Now the trouble with these things is these are charged. Protons have got one positive charge. Positive charges don't like to be next to each other, they repel each other. So if you try and bring two positive things together, there's a force between them pushing them apart. So it's really hard to get two positive things to stick together. It's like trying to put two magnets of the same pole together, they just push themselves apart. So if we could stick two of these protons together like that, we would get helium. And we know that exists, but this doesn't work. This force between these two is too strong, they just won't stick together, they just tear themselves apart. So that's what we'd like to see, that would be helium, and that would be great, but it doesn't work. It's, say, the force between them is just too strong for them to stick together. But this is where the neutron comes in. It's kind of like nuclear Velcro. If you put some neutron in, you can get things to sort of stick together. It's actually a very short-range force that the protons also have, but the neutrons sort of bring to the party. So they bring a bit of extra force, and if you throw one of those into the mix, then it will stick together. And this is what's called helium-3. So there's two protons, that makes it helium, and one neutron, that gives it the 3. So there's 3 particles in it. That's fairly uncommon. There is a certain amount of helium-3 around in the universe, but much more common is helium-4. That's the kind of regular stuff you get in balloons and other things like that. You have to work quite hard to get helium-3. It's a bit of a rarity. So this is really, really stable, because there's enough sort of Velcro to hold these two protons together without them ripping apart. So that appears all over the universe, certainly as helium, but it also appears in radioactive decays and other things like that. So this is a really common thing and really stable. It loves to be in this particular configuration. Now, when the Big Bang went off, there was lots of these particles flying around, and it was really, really hot, at least to begin with. So while the Big Bang was sort of having its thing, and the universe was expanding right at the very beginning, this is in the first couple of seconds of the Big Bang, nothing much happened. All these things wanted to get together to make atoms, but they couldn't. Every time a proton and neutron would try and come together, this would make heavy hydrogen, which you may have heard of, a proton and a neutron. This is just regular hydrogen. One of these particles of radiation, a photon of very high energy, would come in and smash the two apart again. So this stuff will keep trying to form and they get blown apart again. So there's a continual sort of churning over of things trying to get together, but it was just too agitated. It's like sort of being in a blender trying to stick things together, the blade comes around and chops you up again. That sort of thing. That's probably a bad analogy, but we'll go with it. So over the history of the universe, there are certain times that we can break it into. The first bit is the first up to a second. The universe is just far too hot for any of this stuff to stick together. It's trying to come together, but it keeps getting blown apart by this high-powered radiation. At about a second, or perhaps even nearer 3 minutes, the universe has by this time expanded quite a bit and started to cool down. It's now at a few thousand degrees centigrade or Kelvin. And at that point, it's really hot, and it's almost like the interior of a star at that point. You can actually get some of these nuclear reactions to happen, and things start to build. So hydrogens bang into each other and you get helium, and there's a tiny bit goes on to lithium. But at 20 minutes, the universe has expanded even more, and now it's too cold. So we've got this phase where it's far too hot for anything to stick together. This sort of 17 minutes of pure bliss where things can be built, and then at 20 minutes it's too cold. Nothing will hit. You can't overcome the force between these two things to get them to stick together. And so that's kind of what we end up with 20 minutes after the universe has begun. And it stays much like that for at least probably 1 million years. Now, as alluded to, there's a problem. I wasn't expecting that slide, but so this is where Carl Sagan's famous phrase comes in: the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies are made in the interiors of collapsing stars. We are all made of star stuff. Has everybody heard that before somewhere? Carl Sagan quite famously said it. It's good, but it's not completely accurate. I mean, it's quite, it's certainly good enough for the general population that we are all made of star stuff. Other people have said it less poetically. Jim Al-Khalili said we're all made from nuclear waste, which is basically what we are. We're all waste products from stars. Or Chris Impri at Arizona said we're all star bath. You know, stars have been sick and we're the result of that. So kind of which is it? And it's actually none of those. They're all good to a first approximation, that stuff is made in stars, but not everything is made in collapsing stars. Not everything is made quite in that way. So in this talk, I'd like to explain where stuff is made and where stuff isn't made, and how it is and how it isn't, sort of thing. So there's 4 basic processes that generate elements above helium. There's nuclear burning, the S process, the R process, and a couple of other sort of variations on that, and cosmic ray activity. So we'll take each of those in turn. Nuclear burning. This is the easiest, in some sense. This is what's happening in the sun. So we start with these 2 hydrogens, because we've got lots and lots of hydrogen around. 75% of the universe is hydrogen. Nearly 75% of the sun is hydrogen. So the trick is to get 2 hydrogens to stick together, 2 protons to stick together. But I've already told you that can't happen. They've got too much positive charge, so they would just fall apart. But there is a cunning reaction where one of these protons will turn into a neutron. Now, neutrons don't have charge, so a neutron's quite happy sitting next to a proton. There's no repulsion there at all. But you've got to get this funny reaction to happen. Firstly, you've got to get them close enough for the reaction to happen. Then you've got to get this funny reaction where one of them changes its type. It turns from a proton into a neutron just instantaneously. This is driven by the weak nuclear force, if you're interested. And it's really quite a rare occurrence. And in some sense, that's why we're here. Because this is a very rare reaction, this is why the sun burns so slowly. If this was a quicker reaction, the sun would just go woof, and we would all be over in a few seconds. But because this is very slow, this is what limits the rate of the sun. These other reactions that go on to make helium-4, they're a bit faster, but we'll come to those. So this is my tabletop demonstration of what goes on in the sun. This isn't really what goes in the sun. This is what happens on my tabletop, but it's perhaps a good analogy. So I've got 2 magnets, which I've cunningly labelled hydrogen, so that these will repel each other. And sticking on them, I've got a bit of Velcro. And the game is to throw them together fast enough so they stick. If you throw them together too slowly, then they sort of repel each other and veer off. If you were to throw them together too fast, they'd probably break or something like that. The similar thing happens in the sun. If you throw things together too fast, they also don't like it very much. So here we are on my tabletop, trying to get this to happen. You see, most of the time they just go whizzing off into that back there. Once in a while, you get the angle just right, and they stick together. And this is really what is happening in the sun. You need enough heat and enough density so that these two things that don't really want to sit next to each other can come at each other fast enough and just stick just for a few milliseconds. And in that time, this other reaction I told you about, this proton turning into a neutron, happens, and then everybody's happy. Just those two things have to happen at the same time. And just for some indication, so this is the two hydrogens coming together. For an individual atom proton, it's about 10 to the 9 years, about 1 billion years before one of these will happen to run into another at just the right speed and right velocity and everything else and collide. So this is what stops the sun going woof in just a second or so. It takes all this time to get to there. Once it gets to here, things are a lot easier. It's a lot easier to bang another hydrogen into one of these things because, well, nuclear physics and stuff I don't really understand. But these have this is a kind of a much bigger target to aim at, so it's much easier for these to happen. So that takes about 1 second for, once you've got one of those heavy hydrogens, to add another one on, you get a helium-3, then you get a similar thing happening here, 2 helium-3s, form a helium-4, and that's kind of stable, that just sticks around. So this is what the sun is doing all the time, turning hydrogen into helium. Just churning away, but this really slow step stops the sun going off in one big whoosh like an atomic bomb. There are other reactions going on in the sun. This one only just happens in our sun. This happens much better in bigger stars. This is called the CNO cycle, C for carbon, nitrogen, oxygen. And it's kind of like a, what the chemists call it, a reaction with a catalyst. So basically it goes round in a loop here. Carbon goes to nitrogen by addition of a hydrogen. Nitrogen decays to carbon, picks up another hydrogen, goes to nitrogen, to oxygen, to nitrogen, and then a helium comes off. It's a slightly more efficient reaction, excuse me, and goes a little faster and burns quite a lot quicker. But you need about 15 million degrees Kelvin to get this reaction to start, and that's about what our sun burns at, 15 million. So there's a tiny bit of this perhaps going on in our sun, but not very much. Once you get to the really big stars like Rigel or something, this is the dominant thing. This is what's really churning through it. But the trick is you need the carbon, nitrogen and oxygen. So you can't get there until you've already made some of these elements. So how do you make things like that? Well, this is what's happening in the sun at the moment. There's a core right in the very centre, burning this hydrogen into helium, giving off all this energy and giving out the radiation, keeping us all warm. But over time, it burns more and more of this stuff, hydrogen into helium, and you get kind of an ash form in the middle. Helium is heavier than hydrogen, so it sort of sinks to the middle, and it's already being bathed in the middle. So it kind of starts to damp down the star. The star doesn't quite burn as fast as it could. It's like, you know, if you have an open fire, it burns really quite well to begin with, but then you get this big layer of ash and you have to sort of rake some of it out and replace it. So that's what happens in a star. You start to get this helium, and that doesn't burn, at least not at this point. It will burn in a nuclear way, but you need to get much, much higher temperatures. So the temperatures that hydrogen burn at, about 5 to 15 million degrees Kelvin, aren't enough to get helium to burn. So it just sits there, soaking up some of the energy. And this you start getting what's called shell burning. This hydrogen starts to burn in bigger and bigger shells, pushing out. And this is how you get into the red giant phase. The reactions start moving out and making the star swell up. But eventually they will damp it down enough that the star will start to collapse, because you're not burning enough hydrogen to keep the star up. There's gravity pulling it in, trying to squash it into a a tiny area, but it's these nuclear fires that are keeping it pushed out. So it's continual balance between these, and if you get rid of some of this hydrogen burning, the star will start to shrink with this inert helium not helping at all. So the next obvious thing is to get it hot enough, which as the star collapses, it starts to heat up again, and you can get these really hot temperatures, hot enough to burn helium. But the obvious reaction here, which is to take two heliums and bang them together basically and get them to stick, would form beryllium-8. So 2 4s make an 8, and 8 is, well, it's actually element 4, but it's atomic weight 8. So that would be the obvious thing to do, except this is very, very unstable. It's got the wrong combination of atom nuclear bits, protons and neutrons. There's too much force in there for it to hold together. So it falls apart in about a millisecond. If you manage to make one of these, it just drops apart again. So this reaction doesn't really work. It will have a go at it, but it just won't get anywhere with it. What you actually need is what's here called the triple alpha, because these helium nuclei are called alpha particles. When they didn't know what they were, they called them alpha particles way back in history. So what you can do is bang 2 of these together to get a beryllium, and very quickly add another one in before they fall apart. So you've got about a millisecond or a microsecond perhaps to get that to happen. But if it's hot enough, that will happen, and you get to carbon-12. And carbon-12 is nice and stable. It's what makes up most of this room probably. So that's the next reaction that will happen. So we can't get beryllium this way, but we can get to carbon. So that's probably what our sun will do in its late phase, in its late red giant phase. It will start going down this path. Other stars which are much bigger, they get to this much earlier because they're much hotter, so they can start doing this. So this will keep the sun going. In fact, it keeps going for about a tenth of its. If you take a star's life as sort of a unit, if it switches from hydrogen to helium burning, then it gets an extension of its life by about a tenth. So our sun lasts about 10 billion years. It will get another billion years life by burning helium. But it's a reducing game. You can then go on to burn other things, but you need really big stars. Our star will probably stop at this, so we'll get some carbon and maybe some oxygen that we can burn. Bigger stars can then burn carbon into neon and magnesium, oxygen into silicon and sulfur to iron. So they can get reasonable way down the periodic table. So this is how we can make elements. Now, why do we get that? We don't go beyond iron. And this is because of this graph, which I know graphs are scary to some people, but hopefully this wasn't too bad. So this shows you how much energy basically you get out of converting hydrogen into helium. So this is the energy of a hydrogen, this is the energy of a helium. So you get sort of, don't worry about units, you get kind of 7 units of energy. So this is a really efficient reaction. You get some really good stuff out of this. There's a big jump from here to here. You get a lot of energy. When you burn helium to carbon, this is why you only get 10% of the life. It's a much tinier fraction of the energy you get out of it. So it's kind of on its last gasp almost when it's burning helium to carbon. You can then go on to burn oxygen to something like silicon up here. It's an even tinier gap. You're getting much less energy for each of these reactions. And when you look at iron, which is right at the top, that's the maximum you go. As you're going up, you're getting energy out. If you come down, you're losing energy. So if you want to make some of the elements down here, and there's quite a lot, this is uranium down here, these require you to put actually energy in. So the star wouldn't be shining, it would be absorbing light or something to actually get some of these things. So this is where even the biggest stars stop at iron. They can't go beyond that because they haven't got the energy budget to do it. Yeah, see, carbon to oxygen, tiny, tiny amount of things. And in fact, in its last days, often it burns silicon to nickel, and that will keep the star going for an extra day at that point. It's really getting to last gasp of what can it possibly burn to keep it going. You know, it's like you burnt all the firewood, you burnt all the coal, you burnt all the logs, you're now burning the bricks basically of the house. So you're really at the limits there. But this is all happening right in the centre of the sun, so how do any of these escape? Luckily, there's a process that triggers at various stages in the star's life called dredge-up, where it's almost like, I don't know what's a good analogy, boiling milk or something. Suddenly it all becomes bubbling up. And at this dredge-up stage, there's a lot of convection currents within the star, and some of the stuff right in the centre gets pulled up to the surface. And so this gets to expose some of those elements. And we can actually see those in the stars when that happens, because they come to the surface and we can start to detect them. So that's kind of how some of these elements will get out. And this happens in a few places. So this is the life cycle of our sun. So this is the main sequence you may have heard of. This is a standard diagram everybody has to learn in astronomy. So the sun is sitting on the main sequence. When you're on the main sequence, which is this band here, this means you're burning hydrogen. So this is where stars spend nearly all their life. Once they finish that, or they start to finish that, they start to wander off and they go into this red giant phase, which things like Betelgeuse are at now, and quite a lot of other stars. Our own sun will do that, so it will drift off here into this area. Then it goes into a red giant branch where it's a red giant. Then it starts to burn helium down this stage, and it comes what's called the asymptotic giant branch. And then usually it kind of explodes here and casts off a planetary nebula for something like our star, and then descends down here to the white dwarf patch to live out the rest of its life. But at these three key places, you get this dredge-up effect. So it's sort of just rakes everything up, and some of the the elements it's made come to the surface and can be exposed and even scattered out into space at that point. So that's some of how it makes things. But this will only get you to iron, and you need a really big star to even do iron. Next bit is how do you detect this, which is where the talk comes from, metal detecting. So this is from spectra and atomic physics. So this is a toy model of an atom. This is not really how an atom works, but it's good enough that it helps you explain it. So this is the nucleus where the protons and neutrons are, and these are the electrons' orbits. And by laws of quantum mechanics, these are fixed. You can have one here and you can have one here. You can't have one anywhere else. So when the electrons jump between these energy levels, if it drops from here to here, it gives off a photon of light, which is exactly this distance in this separation in energy. If it drops from here to here, it gives off a slightly more energetic one. If it drops from here to here, it gives off a lower one. But for every element, there is a key gap here. So for hydrogen, there's this particular gap. For helium, it's slightly different. So this is why they all have colours, and this is what you can see with spectroscopy. Each of these has their characteristic colours. So you can see hydrogen here, helium there. And just by looking at all these lines, you can work out exactly what element's there. So you can take the light from the sun, split it with a spectroscope, and you can see hydrogen in there. You can see helium. In fact, helium was first detected in the sun before it was known on Earth. So that's how we know what's there. How are we doing for time? I'll just go through this one, S process, and then we'll perhaps have a break for coffee. So this is one of the first processes that can make bigger elements. So we can go beyond iron with this process. And it happens in kind of red giant phase stars in the atmosphere. So up around here in that diagram, this is where this happens. So you usually got hydrogen burning, perhaps helium, and you're forming a core of carbon and oxygen at that point. And there's a couple of reactions which you don't need to know, but I'll put them there just in case you want to, that give off spare neutrons. Now neutrons are really useful particles because they don't have any charge. They can come flying into another atom quite easily if they're on a collision course, and they will just go in and stick because they're like this sort of Velcro. They will come in and stick. They don't have any charge, so they're not repelled like the protons are. They will just come in and stick. And this is how stars like this one are actually producing elements all the while. So it's the S process. So a neutron comes in, and we've got some element here called X, has atomic number Z, atomic weight of A, whatever that is. We add one of these neutrons in, and we go up one level in the atomic weight. It's still the same element at this stage. So if this was carbon 12, this would be carbon 13. It's gone up one element. But then there's a decay process, radioactive decay, and it kicks off an electron, and this neutron changes into a proton. Very similar to the first reaction I showed you. And this just moves you one step up the periodic table. So that would change you carbon into oxygen, I think. Or is it nitrogen? Anybody know their periodic table better than I do? Anyway, it will bump you up one element in the periodic table. And this can happen over and over again. If another neutron comes in, you can also bump yourself up one level in the periodic table. It's very dependent, though, on the exact nature of the element. So this is a case where we're going from silver to antimony. So here's silver. We're taking a neutron. We go up to this isotope of silver, sort of slightly heavier silver, but this is radioactive, and it quickly decays into cadmium. It happens again, and we bump up to cadmium 111. That's stable, so that just sits there quite happy. Same happens to cadmium 112. That's also stable. If you happen to put another neutron in, 113, 114, they're all stable forms of cadmium. If you get to 53, though, this has only got a 53-hour half-life, so in 53 hours, it's got a 50% chance of decaying. This S process, these neutrons typically come along about once every 1,000 years. So at 53 hours, there's very little chance another neutron will come along and bump it up into cadmium 116, which happens to be stable. If it managed to get there, it will be safe. But it never gets the chance. In 53 hours, it will have decayed. It's still waiting another 999 years and however many days. So this will drop down to indium, 115. That picks up a neutron. This is unstable, moves up there. So you can see it slowly chunks its way up the periodic table, slowly getting on. So it's 1,000 years, another 1,000 years. So several thousand years to move along. But stars live for millions of years, or billions of years. So it can do quite a lot of this. This probably forms about somewhere around a third of the heavy elements that we know and love. But there are some places you can't get to. As I say, you can't make cadmium 116 this way because it just decays too quickly for it to get there. And there are some places in the periodic table you just can't get to with this process because you just go through too many unstable things. So tin 122 and 124 you'd never get by this process. So that's the S process. Let's see, what time is it? It's 10 past. Do you want to break now? Would that be good?
Yeah.
Well, go on to the R process. Leave you hanging on the R process. Okay.
Right, won't be very polite, but mad rush to the scene. Okay, mates, and we'll carry on with the talk.
Okay,
thanks.
right. So when we left everybody, we were just finished on the S process, which is the slow process. But so that can only make a certain number of elements, and it's very, very slow, about once every 1,000 years or something for an individual particle. So now we come to the R, which is the rapid process, and this is where most of the Carl Sagan stuff comes true. This is where the big stars explode and make lots of elements. So this is my rather poor animation of a supernova that's going off. So just let it run through once. So this is what's left. This is usually a neutron star or a black hole. And this is the the radiating shell. So what happens is the star suddenly loses all its power because it's just burnt everything it can, and everything collapses in. And through a process that's not really very well understood, it all collapses in, and then it somehow bounces off this core. So it crushes everything really very, very finely into neutrons. So right here, then it sort of staggers around for a bit at this stage, and then nobody's quite sure how it managed to explode. We do see it explode, so we know it does happen. So this is a supernova of type 2, usually, the type 2 supernova. So when that happens, lots of these things are crushed at this point really into neutrons. And so when it explodes, you've got loads and loads of neutrons going around. So it's like the S process. You can add lots and lots of neutrons, but there are so many around that you don't have to wait 1,000 years for one to come along. You get just a rush of them all at once. So it leaps up the periodic table at this point and can sort of jump to the really high elements, even past uranium and things like that that we don't normally see on Earth. So they will decay, obviously, but this is just a reaction that's got so many free neutrons around that it can make all sorts of elements. So you get this rush of neutrons adding on to something like this, makes something that's horribly unstable, got far too many neutrons for its protons. And then you get all sorts of decays happening. So this might jump from sort of atomic weight of 50 to 70 or something like that, be extremely unstable, and then suddenly decay through this process of ejecting electrons and changing neutrons to protons, and it jumps up the periodic table in that process. So that's really what most people talk about when they talk about the birth of elements. It's these big stars exploding. And this is true for a certain amount, but again, there's only certain elements you can make this way. You come against all sorts of limits going up the periodic table from this. So there's a sort of restriction on some of these. And more recently, it's been thought that some of the theoretical calculations underpinning this don't actually work out terribly well. That some of the things that we say, oh yeah, we just make all the elements with this, some of them, they really struggle to work out how we can make them with this process, because there's this big explosion and everything goes out into space. So it's all got to happen very, very rapidly before everything disappears. And this is kind of how it goes. This is the R process. So you go shooting up the periodic table. This is where the stable elements are, the stuff that we know and love. So it goes shooting up the periodic table, and then it suddenly goes under this huge, what's called beta decay, that jumps you up atomic numbers, and then you might go another rush up here and then jump up this way. So it sort of leaps up the periodic table very quickly. And then there's all sorts of funny things that happen, which is really only interesting for people who study this. And this is the S process path going up here. So that's nice, slow, steady, gradual move up the periodic table, whereas this is a real rush up the periodic table. As you can see, this goes jumping up there like that. There is also a theoretical thing called the RP process, which is the rapid proton process, where you get, rather than a batch of neutrons, you get a whole load of protons that come flooding into the elements that happen to be around there. It's a bit more theoretical, and nobody's quite sure whether this actually really happens or whether it's just a sort of physicist pipe dream. Because firstly, it's quite difficult to get these to collide with this, because this is positive, these are positive, so they don't like to hang together. But there's sort of, they're trying to find places where this might happen, and accreting neutron stars is a place I've seen. A neutron star with stuff falling into it is perhaps a place where this happens. So that's just another one, just to sort of complete the tick box of processes. So down here we have the R process. This is the RP process. If it does exist, it sort of goes up this side of it, because you get very proton rich. Up here you get very neutron rich. And up the middle goes the S process. And then there's strange things that happen up here. But outside of these sort of limits, these are just so unstable that they just can't, even if you can make something down here, it's just so unstable it falls apart very quickly. So that's kind of the process they go through. So when people say, oh yes, we're all made in the exploding stars, that's true for a certain amount. There's some of this stuff is true, that we are made in exploding stars. Some of it isn't, that we just this S process ticking along. So more recently, they've looked at other ways to make these, and particularly with just a couple of weeks ago, there's this neutron-neutron star merger. You may have heard about it, it was on the news. They detected with LIGO 2 neutron stars merging. And of course, if you've got 2 stars made purely of neutrons, when they collide, they make a big explosion. You've got lots and lots of neutrons around, so they can make lots of things. So it's long been thought that neutron stars, mergers, or collisions of other things with neutron stars could make lots of the elements. And with this detection, was it 3 weeks ago, something like that, where they had not only the gravitational wave detector detected these 2 neutron stars merging, because they'd got the 3 machines running at the same time, they could say, well, it's just about in that area of sky, and they went and pointed a whole load of telescopes at it, and did indeed detect the explosion remnant in visible light. And then you can do all sorts of stuff with that. You can look at the spectrum of it. And the highlight of it in all the papers was they detected gold. So you can make gold through this process. You make a lot of other elements too, but gold was the one all the sort of tabloids picked up on. So this is what it would look like. This is 2 neutron stars spiraling around each other. They've got a huge amount of gravity. They are the mass of the sun crammed into about 10 kilometers across. So you can see as they merge together here, they sort of coalesce, and then there's a big explosion, and this is where all this neutron-rich stuff explodes out, and you can make other elements. Things that they don't think you can make in the regular supernovas. This is a particular way that you can make certain elements that they don't think you can make from supernovas. And of course, this is very topical because they detected gold in one of these things that was extremely near. This is what they detected. So it was detected by the Fermi satellite in gamma rays and integral in X-rays, I think. It wasn't detected by SWIFT, which was a bit annoying because SWIFT is a telescope especially designed to look out for these sorts of things, but must have been looking the other direction. And with this, almost everybody in an observatory was immediately contacted and said, there's this big explosion and it's probably over there. Everybody go and have a look over there. And there was a number of people who observed the afterglow of it, including actually one of the students at Nottingham just started her PhD. She was doing a summer job in Australia when this came through, and said she happened to be at the telescope, and they said, can you go and have a look over there? So it was a triumph, and the paper giving the details of this detection has 3,500 authors on it. That is nearly every astronomer in the world. Unfortunately, not me. I'm not one of them. In fact, there's a joke going around, between astronomers that, I bumped into someone the other day who wasn't on this paper. So that's me. I'm not on that paper. Lizzie, who was this, just started a PhD, is on the paper. So no sour grapes there. But this is all the stuff that was found. It's NGC 4993 was the host galaxy, which is particularly near for one of these mergers. So they got a lot of good data on it. So this is how we know that certainly in some cases neutron star mergers do produce gold because of all this stuff. And the final way you can make things is something called spallation, which is just a fancy way of saying I'm shooting stuff at other stuff. So it's mostly cosmic rays. So you get a cosmic ray, which is a very high speed particle moving at a good fraction of the speed of light often, usually a proton and an electron, but most of the damage is done with protons because electrons are very weak and feeble. So it comes shooting along at very high speed, hits another atom. Because it's traveling at the speed of light, really, it doesn't worry too much about positive charges, and it just breaks it up. And this is responsible for quite a lot of beryllium, lithium, and boron, some of the low-down ones in the periodic table, so third, fourth, fifth sort of elements are produced this way. Because we said you can't make beryllium by putting 2 heliums together, but you can make other stable versions of beryllium by this process. It's also what gives us carbon-14, which is a very popular isotope of carbon used in radiocarbon dating. So, you know, we all absorb a bit of radioactive carbon-14, and when we die, we can measure how much was in our bodies and give us a date. That's all produced by this method. This is cosmic rays coming into the Earth, and I think they hit nitrogen atoms in the atmosphere and make carbon-14. So there's a continual production of carbon-14 in the atmosphere that plants and animals and dinosaurs and whatever consume, and then lets us radiocarbon date things. So that's the other way, but there's really only a few elements that are made mostly that way. So this is the final version of the periodic table, which is done by Jennifer Johnston. This is actually a Wikipedia version, but this actually gives you sort of the whole scoop on it. So yeah, the blue thing's a Big Bang, so hydrogen and helium. There's a tiny bit of helium made in stars, obviously. That's what they're burning hydrogen into. Lithium by various things, including cosmic rays, so beryllium and boron are mainly made by cosmic rays. We can see these yellow things are exploding massive stars. The silvery ones here, exploding white dwarfs. The purple is the merging neutron stars, so that's changed quite a lot recently. We used to think all of this was supernovas, but now we think quite a lot of it is merging neutron stars. I don't know where we got dying low mass stars, that's the S process, basically kicking in there. So there's quite a lot of detail in this, and it's still being refined to a certain amount. And all these ones here are only made on Earth by particle reactors and things like that, from americium upwards. So that's kind of where we get to with all these things. But now, the last bit of the talk, what does all this tell us about? Well, it tells us a certain amount of things. If you look at a star and you measure how many elements are in it, if you look at a star and all you can see from spectroscopy is that it's made of hydrogen and helium, it must be a really old star, because it was basically made from the stuff left over from the Big Bang. If it's got more metals in it, if it's got carbon in it, nitrogen, oxygen, it must be newer, it must be younger. So this is a way we can date stars. We can work out roughly the age of stars. There are some extremely old stars in the Milky Way. In fact, there's one that's sort of almost older than the universe, but that's more down to the uncertainty in the dating process. But it's called Methuselah's star. I can't remember. It's also got a funny long numeric number. But that was a really old one. So it's one like this. Has mainly hydrogen and helium and very few other elements in it. So we know that's a really old star. Our sun has about 2% of iron and carbon and other stuff in it. So we know it's a much younger star, because it must have been built from stuff that was inherited from supernovas, exploding neutron stars, and all those other processes. So they must have been incorporated in the star when it was built or formed, because it's certainly not hot enough to produce any of those on its own. So we know our star is probably a third-generation star. There was a first-generation star that exploded. Stuff fell into a second-generation star, which exploded, and now we're onto a third-generation star. Probably, that's what we think anyway, for our sun. And there are a few stars with even slightly more metals in it, but around 2% is kind of, they don't get much more than that, because most of the universe is, as I said, hydrogen and helium. So this is what I sort of said before. There's these three categories of stars. There's population 3, which nobody's ever seen. These are stars which would form very soon after the Big Bang. They would be pure hydrogen and helium. They're thought to be extremely big, maybe 100 solar masses, vast things. But because they're so big, they burn through their fuel really, really fast. They probably only last for a few million years, 20 million years at maximum. Sounds a long time to you and me, but 20 million years is certainly not enough time to get life started or anything like that. So these would have burst into the scene, gone really rock star life, exploded very quickly, showered metals and stuff into the galactic medium, and then we get to the population 2 stars, These have low metals, but quite detectable levels of them, maybe 0.01% or something like that. So they've got stuff in them, but they're certainly not the pure ones. Then population 1 stars, which are like our sun, they've got quite a high metal content, and must have come along quite more recently, so they're much younger. So that's how we can sort of date the galaxy as a whole. We look at stars and where they sort of hang out. So this is where population 1 stars like our sun are, particularly in the spiral arms, because that's where a lot of new stars are made. So stars like our sun, we know, are metal rich. They must be young, so they must be forming new. In the very center and out in the halo of the galaxy, this is where we find population 2 stars, which are much older, called metal poor. They don't have nearly as many metals. That probably says something about life as well. If you're going to look for life, you're much better looking around a population 1 star, because it's got a lot of this rubbish, basically. Oxygen, carbon, hydrogen. You can make rocky planets and you can make organic chemistry. There's not very much around these, so it's quite difficult to make rocky planets around those and to have life. So if you're looking for life, go for the population 1 stars, at least if you're looking for life like us. The other thing that affects it quite dramatically is what's called cooling. This is a very busy graph, and there won't be a test on this, so don't worry. But this is how gases can cool. This is the temperature. So when you get up to sort of 1 million degrees Kelvin, this is hydrogen here. So it's quite good at cooling when it's cold. It cools quite rapidly. When it's very hot, it doesn't cool particularly well at all. And this is really important because you need cold gas to form stars. Hot gas won't form stars. It's just too active. It's like feeding toddlers sugary drinks. They just all run around and they won't sit nicely in front of you to listen to a story. They need to cool down and relax to form a star. So typically it can be very hot in galactic environments up this range. But once you get some of these metals like carbon, oxygen, neon and things like that, they really help with the cooling process. When you get more of these metals, it's much easier to form stars. They can suddenly get rid of their heat very quickly and collapse together to form these stars. So cooling is a really important part of this, and there's many astronomers who've spent their life working out these charts basically for how things cool. It also tells a bit about the galaxy. So this is a sort of cross-section of the galaxy. This is the very center of the galaxy. This is kind of the very edge of it. And this is how metals vary as they go. So say it's quite metal poor in the center. When you get about halfway out, it's quite metal rich. There's lots of interesting stuff there. As you go further out, of course, it's much less dense. There's fewer stars around. So if they do explode, there's less chance that those metals will be incorporated in new stars. So there's kind of a sweet spot somewhere around where we are, where there's a lot of these metals and presumably rocky planets and maybe even life. Whereas it's a little more difficult at either end of the spectrum of the galaxy. So these are type 1, type 2 supernovas. Due to the funny way supernovas are classified, it's also type 1b and type 1c. That's a whole different talk. So this is the Crab Nebula. This is where one of these things has exploded, showering these elements out. I mean, this is not only good because it makes them the R process, but it also radiates them out across the galaxy. And there's good evidence that we're sitting in sort of a shell of material that was shot out from a supernova. There's sort of really good evidence that we're in the bubble of a long dead supernova. The other thing we can tell from this is these supernova type 2s, which are these big exploding stars, they very much favour forming what are called alpha elements, which are elements with multiples of 2. So helium, not lithium, boron, not, I got that wrong, not beryllium, carbon, nitrogen, so on, sort of multiples of 2. So you can see that this is a sort of abundance, that's right. So carbon, oxygen are much more abundant than neon. Fluorine is not very abundant because it's an odd number, neon. And this is really about the stability of those helium things. It's very much easier to add a helium onto something because they're very stable particles. So these are called alpha elements. And we can look for these in big areas, particularly things like galaxies. We can look at how many alpha elements. Whereas the other type of supernova that goes off is the type 1a. This is the other type. This is a white dwarf that's in a binary system with a bigger sun, and it steals material off this big sun. So white dwarfs are usually dead, just embers of stars, and they just fade away and radiate, as the song used to say. But if they happen to be in this dwarf system, they can steal material and they can start to grow as this material falls in and spirals in. But white dwarfs are only stable up to about 1.5 times the mass of the sun. Above that, they're too massive and they will fall in and convert to a neutron star. So this is what happens in this case. If it steals enough material, this thing will suddenly, it doesn't actually do that. The process is a little more complicated, but at very close to the barrier where it would form a neutron star, it suddenly, the whole thing catches fire and it explodes with a well-known signature that is what astronomers use basically to measure the universe. But the point about these is they are small, low-mass stars. So to form a white dwarf, you have to start with a small star like our sun, let it burn for about 10 billion years or something, then it forms a white dwarf, and then if you're lucky it will go over into a supernova. So these are very late occurring things, whereas the supernova type 2 are very early occurring. They're big massive stars that burn up their fuel very quickly. So with these sorts of things you can see more iron in them. So this gives us another clue for working out how old things are. Big stars die young, go into one of these core collapse supernovas, give off material very rich in these alpha elements. Whereas the small stars, they live a long time. Some of them will go into these type 1a supernovas and explode, and we can see those. And these give off a lot of iron, particularly strongly. So if we look at very distant things, we can actually measure how many alpha elements, how much iron is in a very distant thing, and use that as some mechanism to work out how, well, it's not really how old the galaxy is, but when it was last active. Because if it's very rich in alpha elements but not in iron, then it's recently had a lot of stars formed. Well, by recently I mean about 1 billion years. They've all gone bang and scattered these alpha elements, but it's not had time yet for these type 1As to occur and start going off. So we can sort of use that to balance things off. So very poor animation, but if it's high in magnesium, which is one of the common things they measure compared to iron, then this means it's very recently been forming stars. Or indeed it's still forming stars because it's giving off these rich alpha elements. On the other hand, if it's something like this, all you see is just the occasional type 1a supernova. This is an elliptical galaxy. They're usually called red and dead because they're not forming stars anymore. And they've got a lot more iron in them and less alpha elements. So we can almost work out when they stopped forming stars, because they must have formed stars because we can see a whole load of them, but it's not forming any new ones. So we can almost work out roughly when that happened. So you can use it as sort of an archaeological tool to sort of carbon date galaxies and see how old they are. So this would be low in magnesium to iron ratio. And this helps us understand this picture, which is still very active research, particularly at Nottingham, where we study galaxies of some form. So there's this big collection of galaxies, spiral galaxies, which are blue in colour, blue cloud. These are medium-sized mass, about 1 billion to 4 billion, 10 billion stars maybe in a spiral galaxy. And then the red sequence, that's all the elliptical galaxies. So they're all very red and dead. And we don't really see very many in between. So somehow they've got to go from the blue cloud to the red sequence, and we're not quite sure how they do that. And this is really a very active area of research. So they could somehow, they could go this way, they could shut off their star formation, which would change it from blue to red, and jump up here and then grow. Or they could grow this way, stop forming stars and go that way, and that's really one of the problems that's taxing quite a lot of the researchers at Nottingham, trying to work out how you can do that. And some of this dating material lets you do that. You can work out when they stopped forming stars using these techniques. This all gets horribly complicated. This also won't be on the final exam. So this is sort of stuff that goes into dating it. There's all sorts of these things that you have to measure. Contributions from dust, chemical evolution, isochrones, all sorts of these things. Typically you get a computer program to do this. You feed in stuff and it sort of goes through all this calculation and works out rough age of it. The ages they give are very, very rough. So you can get sort of 10 billion years plus or minus 20 billion years, something like that. So it's by no means an exact science, but it's kind of the best thing we've got at the moment to date galaxies. So with that, kind of wrap up and leave you with the final version of the periodic table once again, so I think it's quite interesting. So the variation of these, so this has got a bit of purple, some of it's made by merging neutron stars, the rest dying low mass stars. But with that, so the conclusions is, we know fairly well how metals are made. It isn't all in big exploding stars. Some of it is, but quite a lot of it isn't. But if we're using it for working out ages, that's still quite tricky, but we're getting better at it. So with that, thank you very much for your attention, and hope you found some of that interesting at least.
Any questions?
Good. Oh.
Do the merging galaxies story spanner in the works?
Certainly they do, because usually when two galaxies merge, often they've sort of settled down into their kind of relaxed and lying back on their sun loungers, but then they come merging together. That stirs everything up, and you tend to get a big burst of star formation because you get all this gas colliding, and it's suddenly you get hundreds and millions of stars forming. So that's one of the areas they're looking at Nottingham. They're looking for things called post-starburst galaxies. That's often galaxies that have either merged, had this big, amazing amount of star formation, and then we're looking at them maybe a billion years later when that's all sort of finished. So typically you're looking for, if it's just happened, if the starburst happened, you're getting all the stars, so you're getting O, B, A, all the way down. But they generally start popping off. So the O stars go off first because they're the biggest, and the B stars. So when you're looking at a galaxy and you're seeing quite a lot of A stars because they're still quite bright, that's how you kind of work out this is a post-starburst galaxy. It must have happened recently. There's no more O stars and B stars, so that puts the sort of upper limit on how long ago it was. So they're trying to track down a number of these that they're sort of caught in the act of shutting off their stars. So it's tricky.
Anyone else?
Yeah.
Is there an explanation for what actually causes two protons to fuse electromagnetic repulsion at a very close distance? Do you think logically it was simply repulsion would simply increase exponentially to infinity the closer they got? What actually causes the reversal? Then they stick.
There's another force that comes into play basically. So there's four forces there's only four forces in the universe we know of so far. Gravity, we all know about. Electromagnetism, which is the repulsive force in that case. And two, you probably don't meet in everyday life. The strong nuclear force and the weak nuclear force. And the strong nuclear force is what holds the nucleus together. But it only works over a really, really tiny distance, about the width of a nucleus. So if you can get those things close enough, the strong nuclear force will hold them together, except in the case of two protons where there is still too much repulsion. But In that case, it's the weak nuclear force that comes in and changes the proton into a neutron, and then it's all happy. But yeah, you're right, you do need they need to coming in fast enough and get close enough for this second force to come in. But they have to be really, really close for that to happen. So that's kind of where that comes in. There's a whole lot of quantum mechanics, because if you do the calculation, the electrical repulsion is too much for actually two protons to ever meet in the centre of the sun. It should never happen. The sun shouldn't be shining, basically. But when you apply quantum mechanics, there's this quantum tunneling, and they can sort of evade the laws of nature a bit, and they get close enough, and they can sort of jump the final bit. Quantum mechanics is weird. Don't test me on it, because that's about the limit of my knowledge.
Any more questions? Yeah.
You were there first.
Population 2, I think, are about 1.2% metals, aren't they?
Something like that.
Ish. Yeah. Population 1, about 0.2.
Yeah.
Will we ever get to 10 times that, 2, and still be having stars?
I guess you could get to a certain amount. They are affected quite a lot by the metals, so you can understand a star almost completely if you know how heavy it is and what its metal content is. So the more metals, they burn in a slightly different way. So, but at the same mass, they all sort of burn in the same way if they're made of the same stuff.
What I was thinking about is when we get a cloud collapse content, it's going to dissipate the heat a lot more efficiently.
It is, yeah. So I don't know if anybody's looked at that, because
I come up with the idea.
yeah, but so far, 2% is about the limit of what we've ever seen. So yeah, maybe in the distant future there will be, as you say, like 20% or something, and it'll be interesting to know what happens.
Yeah, okay, thank you.
With the neutron star collision, was there any remnant there, or was it just blown inside the bit?
I think there was a remnant. I think it was another neutron star that formed. It was a bit of an odd one, because the two neutron stars were, one of them was quite small. It was about just less than a solar mass, which typically they're usually about 2 solar masses or something like that. Usually one solar mass would form a white dwarf if left to itself. So it's probably something that exploded and sprayed off a lot of material, but the neutron star had already formed at that point. So I think the two collided, a lot of stuff came out, but the gravity on those things is huge. So when they come together, they kind of stick. It's cramming the whole of the sun into about the width of Liverpool, basically. It's that sort of size. So it's a huge amount of material in one place. Say dropping an egg from about this height on a neutron star, you get a thermonuclear explosion with so much force. By the time it hits it, it'll be going so fast that we're just an explosion. All weird, very weird things.
You mentioned earlier on about possibly our solar system or star system is possibly in the remnants of a supernova. What evidence is there for that?
I think it's somewhere in the middle. So I think what they look for is particular isotopes of metals. I think aluminium is one of them. That is unstable but on a long period. So it must have been formed in some process that made it reasonably recently, because otherwise, if it was formed billions and billions of years ago, it wouldn't be aluminium-27 or something like that. It wouldn't still be there. It would have decayed to something else. But it's still enough of it around that it must have been produced reasonably recently. Well, 5 billion years, if you call that recent.
What I'm curious about, I recently purchased a meteorite which contained, the evidence was that it was older than the sun and could only have come, also the elements of that, could only come from a supernova remnant, but that was before our sun was created. It's over 4.5 billion years old. So
yeah, it's quite possible.
It's encrypted with one of the
yeah, I think it would have to contain a particular ratio of these elements. I mean, there was recently a comet or a meteor that came from some other star came in. Yes. So these things do happen. So I'm not an expert on them though, so I can't vouch for your meteorite. There's a meteorite specialist.
Okay. All right.
Thank you very much.
Thank you. I'll call on David to give our views and thanks now.
I'm really glad you said there wasn't a test. Thank you for that. It was absolutely fascinating, especially those of us that are humanities and not science graduates. Particularly like the information about the relatively recent event, the collision.
Neutron star merger.
Well, thank you for making it informative. But you do realise, of course, now that people will be Googling frantically for the most outlandish periodic table.
Yeah.
But can
There's
I
an
have
hour
a
on
applause,
it, I'm gonna
please?
get back.
Right. Thank you, folks. That's all. And see you at the December meeting, which I got down here as Friday the 8th of December. And that will be members' talks on that occasion. So see you next time. Thank you very much and safe journey home.